Hi everyone, I'm Shuichi Hirahara from National Institute of Informatics. Today I would like to explain unexpected hardness result for Kolmogorov complexity. I start with some motivation to study Kolmogorov complexity, and then I will explain our main results. One of the central questions in complexity theory is to separate P from NP. Thanks to the Cook-Levin theorem, it is equivalent to proving that SAT can't be solved in polynomial time. In this sense, in order to separate P from NP, we can focus on SAT, and we can forget about other NP problems. However, Andrei Kolmogorov suggested that we shouldn't focus on SAT, because NP-complete problems such as SAT are too structured to be good candidates for separating P from NP. Instead, we should focus on NP intermediate problems that are complex enough to prove separations. As a specific candidate, he suggested to consider resource-bounded Kolmogorov-Random strings. Let me review the notion of Kolmogorov complexity and Kolmogorov-Randomness. The Kolmogorov complexity of a finite string X is defined as the shortest length of a program for printing X. In order to make it formal, we need to fix a universal Turing machine U that can simulate every Turing machine, and then the time-bounded Kolmogorov complexity of a finite string X is defined as follows. It is denoted by k of x, and is defined as the minimum length of a program D such that the universal Turing machine prints x in time step t given input D. Once we define the notion of Kolmogorov complexity, we can define the notion of Kolmogorov-Randomness. We say that x is Kolmogorov-Random if x can't be compressed to a short program. Here, x is said to be Kolmogorov-Random if the Kolmogorov complexity of x is at least the length of x minus 1. The set of Kolmogorov-Random strings is denoted by R sub k superscript t, where the function t specifies the time bound. Let me provide some two simple examples. If you consider all zero strings, you can compress the string by a short program, so it is not Kolmogorov-Random. On the other hand, if you pick a uniformly at random string with high probability, it is Kolmogorov-Random string, which can be shown by a simple counting argument. With this notion in mind, we can interpret Kolmogorov's approach toward P versus NP question as follows. For a time-bound P, which is a polynomial, it is easy to see that the set of random strings is decidable in co-NP. Therefore, if we can prove that the set of random strings can't be solved in polynomial time, then we can immediately separate P from NP. In this sense, we can interpret Kolmogorov's approach as showing a lower bound for the set of random strings. But what we knew before is that for an exponential time-bound T, the set of Kolmogorov-Random string can't be decided in polynomial time. And it has been an open question to prove it in the case when the time-bound is sub-exponential. In this work, we were able to resolve the question, and we showed that for any superpolynomial time-bound, we show that the set of random strings can't be solved in polynomial time. So far, we have explained a historical motivation to study Kolmogorov complexity. Now, let me try to convince you that it is also important from some technical perspective. The reason why we should care about the complexity of Kolmogorov complexity is that the Kolmogorov-Randomness and Pseudorandomness are closely related. To be more specific, Kolmogorov-Randomness is closely related to a heating set generator, which is one of the central pseudorandom objects. A hitting set generator enables us to derandomize one-sided error algorithm, and our function h is called hitting set generator secure against the class C if the following holds. For any function d, if the algorithm d accepts at least a half of all the input, then there is some seed such that the algorithm accepts the output of the hitting set generator. In the case when d violates this condition, we say that d is a distinguisher for a hitting set generator H. What I'm claiming now is that Kolmogorov-Randomness and Pseudorandomness are equivalent in a certain technical sense. One direction was explored by the work of Arenda et al., and they observed that the set of Kolmogorov-Random string is a very powerful distinguisher that works for any computable hitting set generator. This can be observed by the following two facts. First, if we pick a uniformly random string W, then the string W is going to be a Kolmogorov-Random string with high probability. Second, if you take any seed, the output of a hitting set generator is computable, therefore it is not going to be a Kolmogorov-Random string. By combining these two facts, we can observe that the set of Kolmogorov-Random string is a distinguisher for any hitting set generator. By using this fact, it was shown that the P-space is reducible to the set of random strings. And this was proved by using the pseudorandom generator construction of Travis and Badan, which is based on P-space complete programs. Similarly, next is contained in NP with RK oracle. It is also possible to prove the converse direction of the interplay between Kolmogorov-Randomness and Pseudorandomness. Specifically, if there exists an efficient distinguisher for some hitting set generator, then we can show that there is an efficient algorithm that approximates the time-bounded Kolmogorov complexity. In this sense, Kolmogorov-Randomness and Pseudorandomness are essentially equivalent. Therefore, if we can have a good understanding of Kolmogorov-Randomness, it is quite likely that we can gain some new insight on pseudorandomness as well. With this motivation in mind, let me explain more detailed background of this work. As we explained, there are several hardness results of Kolmogorov-Random strings. For any universal Turing machine, you can show that P-space is reducible to RKU. Similarly, there are several hardness results. For example, exp to the NP is contained in P to the NP to the RK. Somewhat surprisingly, there are limits on such a hardness result for Kolmogorov-Random strings. If we take the intersection over all universal Turing machine, it was shown that there is an exp space upper bound. This is quite surprising because Kolmogorov-Random string is not computable. So if you don't take intersection, there is no computable upper bound. But the point is that if you don't care about a specific choice of universal Turing machine, there is a computable upper bound of exp space. So the class P with RK oracle is sandwiched between P space and exp space. Similarly, NP with RK oracle is sandwiched between NEXP and exp space. It was conjectured by Arenda et al. That the lower bounds are tight and the upper bound of exp space should be improved. In particular, P-space was conjectured to be exactly characterized by the class P with RK oracle. Let me explain why this conjecture seems to be quite plausible. In order to explain that, let H be a heating set generator, and let be a distinguisher for the heating set generator H. By using the pseudorandom generator construction of Trebizond and Badin, it can be shown that P space is reducible to distinguisher D if you take appropriate heating set generator construction. It was shown that Trebizond and Badin's construction is in some sense tight. Gutfreund and Badin showed that there is a p-space/poly upper bound. More specifically, if we take intersection over all distinguisher D, then for any heating set generator whose seed length is at most n by 4, the class BPP with D oracle is contained in p-space/poly. Let's recall the relationship between distinguisher and the set of random strings. The set of random strings is a quite powerful distinguisher, so BPP with D oracle is contained in BPP with a set of random strings. In fact, BPP reduction can be randomized by using the set of Kolmogorov-Random string oracles. Therefore, BPP with RK oracle is actually equal to P to the RK. The point I would like to make here is that in order to improve P-space lower bound, we needed to bypass the upper bound P-space/poly, which was shown by Gutfreund and Badin. Now, let me state our main result. Our result indicates that Kolmogorov-Randomness is much higher than expected. Specifically, we were able to improve the p-space hardness result to exp to the np hardness result. This result refutes both of the conjectures mentioned before under a standard completely theoretic assumption. And this bypasses the impossibility result of Gutfreund and Badin. Let me explain how we bypass the result of Gutfreund and Badin's result. The point is that their result holds if the seed length is smaller than n by 4. In contrast, we consider a pseudorandom generator whose seed length is close to the output length. Specifically, the core of our result is the following main lemma, which states that there is an exp to the np computable pseudorandom generator, such that for any distinguisher D, we can reduce exp to the np to the oracle D. And the reason why this is not subject to the result of Gutfreund and Badin is that the seed length must be n- order log n. Once we prove this main lemma, it is easy to get main theorem, because the set of random string is a quite powerful distinguisher, so we can reduce exp to the np to the set of random strings. Now let me explain how we construct such a pseudorandom generator. In fact, our construction is one of the simplest constructions of a pseudorandom generator, which we call a k-wise direct product generator. Let's take a function f, which is an exp to the np complete problem. And then we take an error-corrected version of f, which we denote by f tilde. Now the direct product generator instantiated with a function f is defined as follows. It takes k inputs, z1 up to zk, and the output is defined as the seed z1 up to zk concatenated with the function value of f tilde evaluated on z1 up to zk. As the choice of parameter k, we choose k to be order log n. What is important about this pseudorandom generator construction is that the advice complexity of the direct product generator is roughly k bits. What we mean by the advice complexity of a pseudorandom generator. In order to explain this, let's review a standard security proof of hardness-based pseudorandom generators. Usually, we start with the assumption that a function f is a Hall function, and then we show that a pseudorandom generator is secure by showing that there is no efficient distinguisher D. Usually, we prove this by taking its counterpositive. Namely, we start with the assumption that there is a distinguisher D, and then we construct a D-oracle circuit that computes the function f. This procedure is usually referred to as a reconstruction procedure. And the point is that the reconstruction procedure usually takes an A bit of advice. So it is a kind of non-uniform procedure. What this means is that given a distinguisher D, there are D oracle algorithms, M1 up to M2 to the A, such that one of them is guaranteed to compute the function f. But the point is that we don't know which algorithm is correct. And if you look at the proof of a security of direct product generator, we can observe that the advice complexity is roughly k, which is order of n for the choice of our parameters. So it is quite small, therefore we can brute force all the algorithms, all the candidate algorithms. With this observation in mind, we can prove the following lemma, which we call enumeration lemma. For any computable function f, we can efficiently enumerate Rk oracle algorithms such that one of them is guaranteed to compute the function f. Now it remains to compute exp to the NP complete function given with the help of these oracles. This can be done by using the notion of selector, which we introduced back in 2015. Namely, we can show that any exp to the NP complete problem admits a selector, which is an efficient algorithm that computes the function f with the help of oracles, one of which is guaranteed to compute the function f. Now, by combining these two results, we can immediately obtain the exp to the NP hardness result. So the idea of using the direct product generator can be applied to other questions about Kolmogorov complexity. Let me explain some consequences of these proof techniques. In the context of Kolmogorov complexity, deterministic reductions are usually thought to be too restricted notion to prove hardness result for Kolmogorov complexity. The reason is that, for example, in the work of Berman and Mayordomo, it was shown that if the set of random strings is NP held under deterministic reduction, where the time bound is exponential, then we can prove that exp is defined from GPP. Therefore, this means that it is difficult to prove hardness result for Kolmogorov complexity and deterministic reductions. A similar result was proved in the context of MCSP as well. Let's consider third oracle MCSP, which we denote by MCSP to the third. In this problem, we are given the truth table of a Boolean function f, and the task is to compute the size of a minimum third oracle circuit that computes the function f. The question of MCSP is related to resource-bounded Kolmogorov complexity because we can regard a minimum circuit size as a kind of resource-bounded Kolmogorov complexity. In fact, it's an open question to prove NP hardness of MCSP with Sator rule, despite the fact that there is a Sator rule in the problem. The main difficulty behind this open question is that we can't prove it by using deterministic reduction, because if we can prove that MCSP with Sator rule is NP hard under deterministic reduction, then we can separate EXP from GPP, which is a notorious open question. So it is difficult to prove NP hardness of MCSP with Sator rule. By using our proof techniques, we are able to prove NP hardness of a related question, which we call mean CKT to the Sator question. This is a question where we are given an input x and y as well as a time bound t, and the task is to compute the conditional Sator rule Kolmogorov complexity of x given y. And we were able to prove that this question is NP hard under polynomial time non-adaptive reductions. The reason why this is interesting is that this is the first hardness result for polynomial time-bounded Kolmogorov complexity under deterministic reduction, which were previously thought to be too restricted notion. There are several other results which we can prove by using the construction of a direct product generator. If you are interested in, please read the paper. To conclude this talk, in this work we presented hardness results for Kolmogorov complexity and a surprisingly efficient reduction which were previously conjectured to be impossible. The key insight of this work is that the otherwise complexity of the direct product generator is quite small. Thank you for your attention.